In this video, we're going over the concepts of noble gas configuration, followed by looking at trends in the periodic table. The noble gas configuration for an atom is going to be an abbreviated form of the full electron configuration. In this abbreviated notation, the arrangement of the electrons start with the noble gas prior to the valence shell electrons in an atom. As an example, previously in a previous video, we saw the electron configuration for sodium. And the full configuration for sodium establishes that the 11 electrons in sodium live in 1s2, 2s2, 2p6, and 3s1. Sodium lives here. And the noble gas that precedes it is neon. What that means is that this area of the electron configuration for sodium, meaning the 1s2, 2s2, 2p6, actually corresponds to the noble gas neon. This 3s1 is the valence electrons that are present in sodium. So to write specifically noble gas configuration, all we're doing is replacing the part of the full configuration that corresponds to the noble gas. We place the symbol of the noble gas in brackets, and then we write the electrons that are part of the valence shell electrons for a particular atom. To illustrate this, we are going to write the noble gas configurations for lithium, sodium, potassium, and rubidium. So we can see that lithium lives here. And let me erase this. Lithium lives here. And specifically, the noble gas that precedes it is helium. 1s2 is the electron configuration for helium. So to write the noble gas configuration for lithium, I'm going to put helium in brackets, and then I'm going to write the valence electrons that are in lithium, which is going to be 2s1. Next, I'm going to do or rewrite the one for sodium. Remember that sodium lives here. The noble gas that precedes it is neon. So for sodium is going to be neon in brackets 3s1. Let me just use my highlighter so you see which part of the full electron configuration corresponds to the noble gas. So in the case of lithium, that 1s2 is helium. This 1s2, 2s2, 2p6 in sodium, that is neon. Let's now move on to potassium and rubidium. If we look at potassium, the noble gas that precedes it is argon. So when it comes to the noble gas configuration, we're going to put argon in brackets, and then we're going to write 4s1. Because the 1s2, 2s2, 2p6, 3s2, 3p6, all of that is the electron configuration for argon. Lastly, when it comes to rubidium, rubidium lives here. The noble gas that precedes rubidium is going to be element 36, which is krypton. That means that the noble gas configuration is going to be in brackets, the symbol for krypton, and then we're going to write 5s1. Out of rubidium, all the way from 4s2 all the way to 4p6, that is the configuration of krypton. And as you can see, we write at the end of the bracket the valence electron for the atom. Let's now look at trends in the periodic table. As we have observed, there's a lot of information that we have in the periodic table. And even though there's many trends in the periodic table, there's only two that we're going to study as part of this course, starting with atomic radius. The atomic radius is the distance extending from the center of the nucleus of the atom to the location of the valence shell of electrons. The trend in the periodic table, specifically for atomic radius, as we can observe here, is that as we move across a period from left to right, the atomic radius is going to decrease. Well, if we move from a lower period number to a higher period number, we can observe that the atomic radius is going to increase. One of the things that it is observed, and at times students wonder, why is it that the atomic size is decreasing when I move across a period, but it increases when I move down within a group? Well, just think about what is happening overall in the atom. When we move across a period, overall, what we're doing is that the number of electrons in an atom is increasing. But along with that, the number of protons in the nucleus is also increasing. Since both of these trends go in the same direction, what happens is that overall, those negative electrons and those positive protons are going to be attracted to each other. And it's going to reduce basically the atomic's radius for that element. The analogy that I like to use is kind of like when students are in a classroom. If there's a student that reaches that energy level, or in other words, the classroom, basically a space, the room looks really large. So that would mean, for example, at period 2, we're dealing with lithium, which only has 3 electrons. Now, as we move across a period, all the way until we reach fluorine, we have increased the number of protons, but also the number of electrons. So using the analogy of students entering a classroom, as more students enter the classroom, the room will look smaller because of how populated it is. While when we are moving from period to period, this is going to be a brand new space. So it's kind of like you're going from the classroom, let's say for the parking lot, or even the middle of a stadium. So since we are in a different place, understand that the room is going to increase. Lastly, the other trend that you need to know in the periodic table is electronegativity. Electronegativity is a measure of the tendency for an atom to attract electrons. When it comes to electronegativity, understand that this is specifically in chapter 5 when we discuss it in detail, but I wanted to use figure 5.6, which illustrate the values that we have for electronegativity. Already, the work for determining the electronegativity of an atom has been created, and this is called the Pauling scale for the scientists that determine these numbers. Overall, understand that electronegativity is going to be increasing as we move across a period, and it's going to be increasing as we move up within a group. The most electronegative atom in the periodic table is fluorine. When it comes to examinations, understand that a table that includes the electronegativity values for atoms is provided. So you don't have to memorize any of these numbers. And whenever you're answering questions like this in the future, please refer to figure 5.6.